Up until now, we've been using simplified methods to design different types of materials in fire, whether it be steel or timber or concrete. And it's methods you can put into a spreadsheet and get an answer relatively easily once you know the principles. But what happens if you have a real fire and a real beam, which you're trying to predict the behavior throughout? The sort of thing you would do in research. So you'd run an experiment, you'd have a structural element, it's exposed to a fire, and you want to know, how does it behave throughout, and can I predict what happens? Can I predict how it deflects and where it cracks and what that sort, and all those sorts of behavior? So we're going to be doing a very brief introduction into advanced modeling of structural elements in fire. And I'm just going to take as an example a concrete beam. And let's say there's some rebar in it, and we're going to now have a look at how would we model this and what might be this sort of things we'd be looking for. Because firstly, we need to discretize this into various elements. So depending on the size of it, we'd come up with a mesh and break this up into a larger number of small pieces. And then each of these pieces will have stresses and strains and temperatures and the likes. And whether you realize it or not, up until now we've been doing what's called a decoupled analysis. So first we calculate temperatures in either from a simple model or tables or from whatever it is, spreadsheets, and then we apply it to a separate structural model. So it's a decoupled thermal and then a separate mechanical analysis. But you can also do a coupled thermomechanical analysis where in one piece of computer software you then both determine the temperatures through the section and then how it behaves. And you can still use this cross-section I've shown separately, use a cross-section to get the temperature and then a separate model for structural resistance. But let's say we're now going to do a coupled analysis. So we would now apply a fire to the section. We'd apply heat fluxes and convection heating all the way around the outside. And then there would be conduction through the section, and after a certain period of time we'd have different isotherms with temperature into our section as it heats up. And then from that we pick up the temperature, and now we can start analyzing it. And then we can start predicting as it expands due to the higher temperatures, what do the stresses and strains look like. But also we need to couple our material resistance, because the Young's modulus and the material strength will adjust. So if I have a little element here, and this is now at 600 degrees Celsius or 400 degrees Celsius, both my strength will have reduced and my Young's modulus. So I'd have to adjust it, and then do that for all the different elements, and they're going to be interacting, because as one piece is expanding, it might be then putting the adjacent piece into tension or compression. So let's say now I took a cross-section through there. Let's start seeing what could we potentially expect to see. What are some of the behaviors that might emerge that would possibly even be counterintuitive, but just quite difficult to predict, especially with simple models. So if I draw the temperature through the section and over the height, it would be very low in the middle, and then as it gets towards the bottom, then rapidly increase. Something like that. So we'd have high temperatures at the face, and then those would quickly decrease, especially for concrete, which is a good insulator. And then our thermal strains would look more or less the same. So epsilon theta, that is our temperature, and so that is our thermal strain. So either this would be the same, roughly the same for our temperature and our thermal strain graph. So that's a profile that would look like. So this is wanting to expand, and not much is happening up there. But if we have a look at what would that do to the internal stresses in our cross-section, and if we just took a cross-section, I'm going to ignore what's happening on the left or right. Let's just say it's a uniform temperature profile over the whole depth. Now, as it expands at the bottom, it's going to then put the top into tension and then put the bottom into compression. But at the same time, some sections are weakening. So we can have very, very complex behavior. And for instance, I'll draw an example, and it can be a lot more complicated than this. So this is my stress graph with height. We may have compression at the bottom, going through to tension, and then back to compression. And that's not the normal stress strain graph you see, and it's simply because you have this interaction of parts that are heating up and then parts that fail, and then the remaining is the remaining of section is being forced into tension compression. And this is then further influenced by external applied loads. You've got compressive loads or moments or whatever it is. And the fact that as this expands, it might expand against the structure around it, creating additional restraining forces. And then there are even other factors that occur. For instance, if our rebar is here, and it's got, well, the stress would be much higher than the concrete, but it's in tension here, it may cause this area to fail, and then the concrete around it that is basically stuck to this rebar will increase its stiffness. So the stiffness of the rebar would actually increase over and above just that of the bars, and we have what's called tension stiffening in the bars. And all of these factors would be occurring in our beam, amongst others: complicated stress-strain profiles, temperature distributions, and this is just over the height, then I've got over the breadth. So those are all the different factors, all the different phenomena happening within my cross-section. So it makes the accurate analysis of cross-sections in fire possible but complicated. And if you wanted to do this, this is more for research. You might want to, in certain scenarios, do this in practice, but the time and effort required is normally quite severe. But also you need to know quite a bit about the section, where the rebar is, concrete types, materials, and then also the computational effort gets quite heavy, because this is just for one cross-section. If you're doing it for an entire length of beam, you'd end up with a lot of elements and quite a high computational effort. But if you are looking for accurate, well, more accurate deflections and stresses and strains, you do need to get to something like this. So this is just giving you an overview of what can be done. And as I said, you can either use this model just for the thermal analysis, getting temperatures, or combine it thermomechanical, or have a separate mechanical analysis. All different options that you could potentially apply when carrying out more advanced analyses to understand the behavior of structures in fire. Thank you.